So, we've now dealt with two types of reactions, double replacement and redox. Double replacement and redox. Those are the only types of reactions that exist, actually. I know I said five, that there were five of them, but really it's kind of a simplistic way of looking at it. There are three types of double replacement. What are they? Precipitation. Give me another one. Acid-base. Give me another one. Gas-producing. Now, there are four types of redox, and we've only covered one. The only one we've covered is single replacement. Actually, you're right. Combustion is one that we've covered since day one, and there's two more we're going to go over today. Synthesis and decomposition. And those are the two types of reactions, double replacement and redox. Today, let's focus on synthesis and decomposition. Three more kinds of redox besides single replacement: synthesis, decomposition, and combustion. First one up, synthesis. Synthesis. This is, I believe it was Mark getting married to who? Natalie. Mark and Natalie. Mark plus Natalie forms Mark and Natalie Holthausen, right? Analogy, marriage. Marriage. Let me give you several examples and demonstrate to you that they are redox reactions, believe it or not. And then I'll actually show you video of three of them. I think three of them. First of all, one of the most famous of these redox reactions is the space shuttle fuel, hydrogen and oxygen. This is the same fuel that we're going to use for our rocket ship lab on Tuesday. Space shuttle. You guys have never seen a space shuttle take off, have you? It is so sad. On video you have, right? It's so sad. Those of us who survived the space race, it is terribly disappointing to us that the Russians, the people that we beat, are the ones carrying our astronauts into space. Maybe with the new election, we'll have a president that will take a longer look at the space agency and give them more money. Hydrogen and oxygen combine to form water and the release of oxygen. Hydrogen plus oxygen to form water. All right. Is it balanced? Grant, balance it. How many oxygens?
2.
How many oxygens?
1.
Balance it.
You just put 2.
Yeah, but that screws up your hydrogens. Okay. Now, let me show you that it is a redox reaction. Any element that it's in its natural form has a charge of 0. Any element in its natural form has a charge of 0. Any element that's part of a compound will have its normal charge. So the normal charge on oxygen is? Normal charge on hydrogen? +1. Okay. This should become clear. Grant, hydrogen is going from 0 to +1. Oxidation or reduction?
Oxidation.
Which makes it what kind of agent? Reducing agent. Oxygen is going from 0 to -2. What happens to it?
Reduction.
What kind of agent? Oxidizing agent. Yes, Morgan.
So would we like not have to do the little parentheses with aqueous or
Well, yes, in reaction prediction. Okay, I'm glad you brought that up. I am not going to make you guys predict synthesis or decomposition reactions. They are a little squirrely, and that's not a bad. And frankly, I've got to let Eddie do something for himself. Okay, I pretty much teach most of what AP Chemistry is all about, and he just reaps the reward. So some harder topics I let him deal with so that he could feel like he's earning his keep. All right? And how to predict synthesis and decomposition reactions. This one's easy, but how to predict synthesis and decomposition reactions is one of those things that I leave for him to do. But can you not see that this is an oxidation reduction? Yeah. Okay, this is two elements becoming a compound. But can you have a compound and an element marrying? Yes. Carbon monoxide plus oxygen by itself yields carbon dioxide. Noah, is this balanced? Balance it then. Okay. Very good. All right. Let's figure out who's being oxidized and who's being reduced. Noah, carbon. What is the charge on carbon? We don't know. So we're going to have to rely on oxygen to let us know. What is the charge on oxygen? Okay, if oxygen is -2 and carbon is balancing that out, oxygen by itself has a charge of carbon. We don't know. So let's see what oxygen is. -2. 2 times -2. So what must carbon be to balance out -4? To balance it out. How can it be negative? +4. All right. So what happens to carbon's charge? Goes up, making it the one that was? What kind of agent? Thank you, Noah. You have an echo. All right, oxygen goes from -2 to -2. Nothing, right? Didn't go up or down. Uh-oh. If somebody goes up, somebody must come down. How about oxygen here? 0 to... Yep, that's the one that was reduced. Oxidizing agent. Very good. Very good. Example number 3. Here's another element plus another element. Is sodium a diatomic? No. How about chlorine? Beth, is chlorine a diatomic? Beth, and Beth does not need an echo to form sodium. Is that right? Is that the formula for NaCl? 2? No. But do you see how very easy it is to do that? Do you see how easy it is to go, well, that's a 2, so that must be a 2? No. No, Beth. +1 minus 1. That is the correct chemical formula. But Beth is upset because she sees there's a 2 here and there's not a 2 here. How can we handle that the correct way, Beth? Very good. All right. Beth, sodium by itself, charge. Try again. By itself, charge. Chlorine by itself, charge. Sodium, part of a compound, charge. Chloride as part of a compound, charge. Sodium goes, making it what kind of agent? Chlorine goes, what kind of agent? Very good. All right, let's see some of these. This is hydrogen reacting with oxygen. And do you think this is exothermic or endothermic? That's under the category of duh, right? Do you see why it is such a good fuel for using in rocketry? Okay, and what is its waste product? Water. Water. This yellowish gas is chlorine. I know it's hard to see because of this reflection, but there is a piece of sodium sitting right there. Now, in order for it to react with the chlorine, it needs to hit the activation energy hill. They're going to do that by just having sodium
And what we're going
react
to do
with water a second.
is I'm going to drop some water on this sodium metal to activate it. And we should see a pretty brilliant reaction once I activate it. So I'm just trying to drop some water with a pipette to start the reaction. And there it is. And that white smoke you see is sodium chloride solid. It's a colloid.
It'll eventually settle down and become something that you can sprinkle on your French fries. Isn't that crazy? That is crazy. No. This is aluminum, and they're going to add bromine to it. Bromine liquid. It's a brown liquid. Watch. So you see that colorful mess, and yet, what does it form? It forms a white crystal. Crazy. All right, let's deal with some decomposition. Alas and be sooth does the marriage of Mark and Natalie Holthausen last. No. Natalie wanted to watch Doctor Who. Mark just wanted to watch sports. They just realized that they really didn't have a lot in common. So pretty soon that just kind of created a rift. And yeah, they got a divorce. They got a divorce. I'm so sorry. I'm so sorry. Divorces are terrible. At least you didn't have any kids. But you did have a dog. Who kept the dog? Okay, Natalie kept the dog.
No one.
This is mercury oxide. This is a beautiful orange crystal, mercury oxide. Doesn't look like much is going on until you follow the test tube. The test tube is attached to a tube that is running underwater. And yeah, bubbles are being created. Those are oxygen bubbles. And the mercury metal is what you have on the other side. Now these are also redox reactions, but they're unusual. Watch. Mercury 2 oxide. Is mercury a diatomic? Molly? No. How about oxygen? But that means it's not balanced. Tough, balance it. Yeah, but now you messed up HD. All right, now let's see who is reduced and oxidized. Up until now, every metal you've ever dealt with was oxidized. How about mercury? Let's see. Mercury can be either +2 or +2.
+2.
This Roman Mercury 2 will not have the little 2 down here. Mercury 1 will. Okay. Mercury 1 is 2 Mercury 1s tied together. Siamese twins. So the total is Mercury 2 plus 2. Mercury 2 is what you would think Mercury 2 is. Okay, so Mercury, Molly, by itself in its natural form. Oxygen by itself in its natural form. All right, so what happens to mercury? Mercury goes, uh-oh. So mercury was in decomposition reactions like this, because Mother Nature does not like to break down. Mother Nature likes to make compounds. Mother Nature does not like to break things down into its element form. So this is kind of like reverse engineering for Mother Nature. So metals are usually oxidized. If you decompose them, the metal will be reduced, making it the, Molly? And what happens to oxygen if it goes from -2 to 0? Isn't that crazy? Oxygen got oxidized. Oxygen got oxidized. Here is water.
First of all, add some regular tap water.
This guy's
to
a
that.
little quirky, but it's still
Or, I know everybody thinks that water itself conducts electricity, but the fact is that it doesn't. If you took purified water, it would not conduct electricity. What does conduct electricity are the ions dissolved in water. So we need to make sure that we have enough ions here so that electricity can flow through the solution. I'm just going to add magnesium sulfate. You probably know it by the name of Epsom salt, which you can buy in any drugstore or grocery store. I'm just going to use a test tube to stir. Okay, and that looks salty enough to me. I'm using this 9-volt battery, which you can buy pretty much anywhere, and I'm just going to lower that into the solution. It should start to electrolyze the water. It's working. Gas is forming at the electrodes. One of the electrodes is forming more gas than the other. And that's because ratio of hydrogen to oxygen is 2 to 1. So we're going to be forming twice as much hydrogen as we are oxygen. So we can therefore conclude that the electrode on the right is the one producing hydrogen, because we would expect more hydrogen to be formed. And we can actually look at the relative ratio by placing test tubes over the electrodes to capture the gas. So I've just filled these test tubes with a solution, so we're going to see how much of that water actually gets displaced. The test tube on the right has twice as much gas as the one on the left.
All right, so why do you get twice as much hydrogen? Because let's look at a balanced equation. What is water breaking down into? Hydrogen gas and oxygen gas. But when you balance it, what happens? You get twice as much hydrogen as oxygen. And that's why you had twice as much bubbles. That's why you had twice as much gas being produced. All right, one last one. Some of these decomposition, remember I told you this goes up against Mother Nature, which makes it a little tougher for these reactions to get going. So oftentimes you need a catalyst in order to speed up the reaction by lowering the activation energy hill.
Mr. Brandon,
Yes.
was the water the catalyst?
No. For the last reaction?
No, for the one where he dropped the water.
No, that was kind of like a side reaction in order to get the temperature hot enough. All right. So we'll have to watch this. All right. Let's review very quickly. There are only 2 types of reactions. There are only 2. What are the 2 types of reactions? Can somebody give me one? Yes.
Redox.
Yes. Redox. What's another? Mark. No. Combustion is an example of redox. Beth. Double replacement. What are the 3 types of double replacements? Precipitation. acid base. And gas producing. 3 more redoxes.
Yeah, that one.
Decomposition. Single replacement.
I got that one already.
Synthesis. Okay, so synthesis and decomposition is what we covered last. Synthesis is marriage. A plus B forms AB. Decomposition is divorce. AB yields A plus B. Single replacement is tapping a dance partner out, right? A plus BC yields AC plus B. Combustion is the last one.
Ooh, I got the combustion.
What is it?
Hydrocarbon plus oxygen yields water and carbon dioxide.
That was good.
That was awesome. That was awesome. It is both the first and the last, the beginning and the end. It was the very first reaction that I actually did for you guys. It was the demo where I shot the cork across the room, right? Who did I try to hit in this class? Mark.
No.
Mark.
No, you shot Mark by accident.
And I hit Alec by accident. Wow, 2 for the price of 1. Okay.
Mark, so it's just one.
So, combustion reactions. Whenever hydrocarbons react with oxygen gas, it will form carbon dioxide and water, just like Ryan told us. What is a hydrocarbon? Well, a hydrocarbon is a compound made up of hydrogen and carbon. Now, why is it not called hydrogen carbon? Probably because it's just a whole lot easier just to call it a hydrocarbon. It sounds cooler. Now, it will react in air. But I hope by now you're beginning to realize that there is a lazy part of air and then there's the reactive part of air. What's the reactive part of air? Oxygen. Okay, most things would prefer to react with oxygen. Nitrogen is actually kind of inert. Think of them as kind of a ugly gas. Most people will not react with them unless they have no other choice. I know, that's brutal, but true. All right, here we go. I used to do a demonstration similar to this until the fire marshal got a hold of me and
One of the reaction types that you're going to learn about is the combustion reaction. Now, you've probably heard about combustions in automobiles where you combust gasoline in an engine to produce energy that makes your car go. And your gas furnaces at home actually combust gas to give you heat that heats your homes. Well, today I'm going to demonstrate a combustion reaction right in front of you. Okay, this is called methane bubbles. I'm just generating some methane bubbles right now. So that looks to be enough, so I'm just going to come over here and turn them off. Now, when we have a combustion reaction, we have to have what we're going to combust, which is the gas inside these bubbles, and we need an ignition source. So what I have is just a lighter here. I have some methane bubbles. I'm going to ignite them. Okay, so here we go.
okay. I used to have a scorch mark on the in the other building. Unfortunately, once I got in here, I looked at all the sensors because this fireball actually would expand over several feet. I would not do it from the hand. That always kind of unnerved me. So I would let the bubbles actually rise up, and then I would ignite them with a meter stick, and would create a beautiful, beautiful fireball that was relatively safe.
Wait, how would you ignite it with a meter stick?
I would have a candle on the tip of the meter stick.
Oh, that's cool.
And so the fire marshal was doing a tour of the building, and I said, hey, come in here. Can I do this? And I did it, and she goes, no, don't ever do that again. I go, why?
Why you ask?
I know, I should not have asked. The sprinklers have a glass tip over a piece of wire, and if that glass tip gets hot enough, it will set off the sprinklers. Because the glass tip will melt and expose the wire, and that's what sets off the sprinkler. So she said more than likely it would be all right, but if it does set off the sprinklers, then everything gets wet. And I will be in big time trouble, so I said, oh well, I'll show them a video. All right, let's do 3 examples. Dicarbon dihydride. The hardest part here is really coming up with the chemical formula for the hydrocarbon. Dicarbon is
2,
dihydride
2,
plus, well, it didn't say oxygen. Should it be oxygen? Yeah. I don't have to tell you oxygen. It has to be oxygen. So if it's burning in air, or if I just say combusting, it has to be oxygen. To form, according to Ryan, carbon dioxide and water. Now we need to balance. 2 carbons, 2 carbons. 2 hydrogens. Oh, there's 2 hydrogens right there. And that makes me stop. This number has to be an even number. Because if it's not, then there is no way in the world that I can balance it. Because here I am trapped. Oxygen has to be an even number. So 2 times 2 is 4. Odd number 1 makes it 5. I can't balance it. So if I ever put an odd number here, I stop, I erase everything, and I go back and put a 2 here. So that's the only way it's going to work. Let's try it now. 2 times 2 is 4. 4. 2 times 2 is 4. 2 times 2 is 4. Now it will work. 4 times 2 is 8. And 2 more is 10. 502.
Like you said, no odd number.
Yeah.
This is not an odd number.
No, but 5 is.
Yeah, so it makes it. This is the problem child, because if this is, let's say this is 3, then that gives me 3 oxygens. There's no way that I can balance 3 over here.
What about the CO2? Can that be as?
This is the only problem. Any one of them can be an odd. If that sucker is odd, we've got problems. And even if this is odd, what does 3 times 2 make the oxygen number into? 6, which is okay. It has to be even. Both of those numbers have to be even. Okay, so one last question for you. How in the world is this a combustion reaction? I don't know. Let's put charges down for everything. Grant. Carbon. What is the charge on carbon? The answer is, I don't know. We don't have charges on our periodic table for carbon. Carbon is a chameleon. Carbon can be, Grant, whatever it needs to be. Hydrogen, more often than not, is what? Grant.
+1.
Okay, so if you have 2 plus 1s, you have a plus 2. What if the whole thing has to balance back out into 0? What must carbon be in order to balance out with the plus 2? 2 minus 1s is minus 2. You're correct. Grant, oxygen by itself has a charge of. Try again. Anything by itself has a charge of. Carbon here. You best not start with carbon. Carbon is a chameleon. What is the charge on oxygen when it is part of a compound? 2 times -2. What is the charge on carbon if it must balance out the -4? Very nice. Hydrogen charge. Oxygen charge. All right. So carbon goes from -1 to +4. Is that a rise or a fall? So it is oil rig. Oxidation is losing electrons, reduction is gaining. So when you lose electrons, you become more positive. Hydrogen's going from +1 to +1. We can't call it a spectator ion, but it kind of is. We can't call it a spectator ion. Why? This is not a watery double replacement reaction or a single replacement. It's not watery. It doesn't happen in an aqueous solution where these ions can disperse. Okay, oxygen, Grant, goes from 0 to, so it's going down. So we call it, gang, it doesn't matter what type of combustion reaction you have. The carbon will always be oxidized and the oxygen will always be reduced. Period. End of story. Always. Carbon is oxidized and oxygen is reduced. All of these are reduction oxidation. Bethling, tricarbon octahydride. Plus, how did you know? I didn't tell you that it was reacted to O2. To form? What two things does combustion reaction always result in? CO2 and 3. Is this a problem that that's an odd number? No. This is the one you need to watch out for. 8. Are we okay? We're okay. We're okay. If that was a 5, then we'd have to start all over. 3 times 2 is, Beth, plus 4 more. What times 2? Which one of these is oxidized? Let's go back and review. The carbon is always oxidized, and the oxygen is always reduced. Oxidized, reduced. Yep. Marieli, este para mí, por favor. Dicarbon tetrahydrido. Deca is 10. Two carbons, 4 hydrogens. 4. We're safe. We're safe. 2 times 2 is plus 2 more. What times 2 will give us 6? Which one is oxidized? Which one's reduced? Okay. That is combustion reaction. We're done with that target. It is easy. But let me complicate things a little bit. Don't worry. This is still easy too. Okay, here's the situation. That is dicarbon tetrahydride. Those dashes refer to electrons that are being shared. In reality, these guys don't have any charges because there is really no giving and taking when they are in this form. Now, there is giving and taking when they react, But in this form, they really don't have a charge. The reason why we say that this is, well, +1, +4, -2. The reason we call this -2, we say that carbon is -2, is to help us understand what is going on. It really doesn't have a -2 charge. It doesn't have a charge at all. It's sharing electrons. So what do we call this? We call them oxidation numbers. So I need you to be able to figure out the oxidation numbers for these things. Eventually, AP chemistry and college chemistry will require you to go far deeper into oxidation reduction than we're going to go in honors chemistry. Some metals and nonmetals will undergo redox in a way that is harder to predict. So we imagine what their charge is. Their imaginary charges are called oxidation numbers. They're charges out of convenience. Okay, they are the charge that helps us understand what is really going on, when in reality they don't have a charge at all. So oxidation numbers, I like to think of them as imaginary charges. So I'm going to, from now on, give you either ions or compounds and ask you to find the oxidation number of the oddball. First, in order to do this, we need to decide what we know for sure. We know that oxygen is 98% of the time -2. The only time that it is not -2 is in the form of peroxide. If you have two oxygens and together they have a -2 charge, what must each oxygen have a charge of? -1. Okay, so unless you're dealing with peroxide, oxygen is -2. Hydrogen is always +1 unless it's acting like a girl. Hydrogen is actually a girl, a nonmetal, that acts like a guy most of the time. But sometimes she wants to act like a girl. And she will act like a girl if she is bonded to an alkali or an alkaline, in which case she is -1. But most of the time she is +1. +1. We're talking 98% of the time. Okay? Alkali, 100% of the time will become +1. Alkaline, 100% of the time will become +2. Halogens, -1, 100%, 98% of the time. If it's acting normal. Okay? If it's acting where it should be. If it looks like it's where it should be, it'll be -1. Okay, I like to think of these two types of things as either pizza or a sandwich. You know, a sandwich is made up of two breads and a meat. The meat is always the mystery. I call it mystery meat. Okay? And pizza is made up of breading, which is the dough, right? The crust. And if it's a real pizza, there's going to be meat. You veggies, okay, fine, whatever. For me, if it's a pizza, there has to be some meat. That's right. It's salad with some breading on it. All right. Here is an example of a sandwich. Why do I call it? The bread are the atoms whose charges are easily recognizable. Bread, bread. What's in the middle? Mystery meat. Na2CrO4. Notice that this is a compound. That means everything's been balanced out, which means everything has to equal 0.
+2.
Okay, here we go.
Right?
Sodium is acting normal. Oxygen is acting normal. This is our X. What is the charge on sodium? No. Plus 1. 2 plus 1s is? Such a cute sneeze. It's adorable. Oxygen's charge is? 4 times -2. Okay, this chromium must balance everything out. So, 2 plus x, 2 plus what, minus 8 equals 0. Plus 6. Do you have to have a plus? Yes, you do. Just like you have to have a minus, if it's a minus. Any questions? Yes. Here's a harder one. Why is it harder? Because of that 2 there. It's no longer just x. It's going to have to be 2x. 2x. All right. K2Cr2O7. Notice there's no charge, so the whole thing has to equal 0. The breads are the ones whose charges you know. What is the charge on potassium? 2 times plus 1. Oxygen is acting normal at the tail end of this thing. 2 times -7. Now, what makes this one hard is that we're looking for x, and there's 2 of them. So 2 plus 2x must balance out the 14. 2 plus 2x must balance out the 14. 2x is equal to 12. X is equal to sandwiches. Sandwiches. And you're trying to find the mystery meat. Now, let's do some pizzas. MN, look it up. MN can be anything. MN is in italics. MN is your mystery meat. Which means that oxygen is acting normal. Now, what's different here? Yes, on the last one, we had they all equal 0. Now, the whole thing has to equal -1. All right, so if manganese is our X, oxygen, we should know what it is. What is the charge on oxygen? 4 times -2 is? Okay, what must X be? Once it reacts with the -8, gives us -1. So it's not a complete balance. The answer is? Now, this one's a little harder. What makes it a little harder? You got a 2 there. The whole thing has to equal -2. So, carbon, what's the charge on carbon? I don't know. Carbon can be whatever it needs to be. Oxygen, what is its charge? 4 times -2 is 2x. Must not completely balance out the 8. It needs to come too short from completely balancing out the 8. So, 2x minus 8 equals -2. The answer is +3. Yes?
Is smoke water vapor?
Smoke?
Yeah.
No, smoke is solid particulates. Just solid particles that just get dispersed in air. It's the leftovers from an incomplete combustion of tobacco. All right. That is target 8.7, and that is the end of this chapter.